Okay, so science regards the sun as a big ball of plasma. Plasma being the fourth state of matter, when a gas gets so hot that the protons and the electrons and the atoms split apart. And the solar plasma that makes up the solar atmosphere, you can just kind of see around the edges, is modelled, perhaps surprisingly, as a fluid, just like water. And like any fluid, it actually has some kind of viscosity. And now we all have some kind of intuition about viscosity, right? We know that honey is somehow thicker or more viscous than water. You can actually put a number on that. You can say that water is actually about 10,000 times runnier than honey, sorry. And the solar atmosphere is actually about 100,000 times runnier than that. So if you want a good fact to take home, it's that the solar atmosphere, this big ball of burning plasma, is about 1 billion times runnier than honey. So where does viscosity come from? Viscosity in a regular fluid comes from just particles bouncing around the fluid, banging into each other. So imagine yourself on a busy high street and you're trying to get from one shop to the other and you're trying to cross but you keep banging into people. That's viscosity in water, right? Particles struggle to get from one place to another, and so they're slowed down by viscosity. Honey, particles actually try and stick to each other, so it's even slower, it's even more viscous. The sun starts getting a bit freaky because the viscosity in the sun doesn't just work in a normal way, because as well as being very, very runny, it's just because the particles are so far apart that they don't really crash into each other as much. The particles in the sun like to stick to the sun's magnetic field, so they actually tend to travel along and back the magnetic field, which you can actually just kind of see these strands here. And so there's much more chance of them crashing into each other when they're traveling around these magnetic fields than if they move in other directions. And so that's where this anisotropic behaviour comes from. Anisotropic meaning just different behaviour in different directions. So what does that actually mean? What does that actually mean for the sun? What does it mean for us? Well, for the sun, you actually find if a fluid is like the solar atmosphere is runnier in one direction, it will go faster in that direction, right? So we actually have greater speeds, we can have greater energy releases, and we can have much stronger, brighter flares, such as these brilliant explosions of solar radiation. And so what does that actually mean for us? Well, it means these flares are actually pretty interesting when it comes to interacting with the Earth magnetic field. We get these auroras, but then they can also perhaps affect negatively satellites and astronauts that exist outside the protected magnetic field. And so understanding anisotropic viscosity is really crucial to understanding these behaviours and being able to protect against these massive solar phenomena.